Okay, good evening everyone. Today we'll discuss week 12 of the aircraft design course. So let us proceed. So in this week we'll just solve some exercises. So this is the first exercise. So this tells us, so we read the problem statement. It says that given a general aviation airplane as shown in figure 2.16, determine the contribution of the wing, tail, and fuselage to the CM versus alpha curve. But like here we are going to ignore the fuselage effects, so you can ignore this. So we'll find the contribution of wing, tail to the CM versus alpha curve, and also we'll determine the stick fixed neutral point. And for this problem, we assume standard sea level atmospheric conditions. So all this data has been given. So the weight, the velocity, and the position of the CG. Okay, and then we have been given wing airfoil characteristics. Okay, and the tail airfoil characteristics, and we have also been given the geometry of the wing. So the first thing that we'll do is we'll find out the aspect ratio and we'll calculate the CL alpha 3D. So these numbers which are given CL alpha for the wing and the tail, these are CL alpha 2D values. So we'll calculate CL alpha 3D. So for that, so let me first write wing. So for the wing, we'll first find out the aspect ratio. So aspect ratio is equal to B square by S, and this is for the wing. The For wing, your B is 33.4 and S is 184. So this is will be 33.4 square by 184, and this comes out to 6.06. And your CL alpha 2D is given as 5.5581 per radian. 0.55. So this is given in degrees. You have to convert it into radians, and for that you have to multiply by 57.3. So wait. So this comes out to 5.5581 per radian. Okay, and next, wait 1 minute. So okay, so now CL alpha 3D is equal to CL alpha 2D by 1 plus CL alpha 2D by pi E into aspect ratio. Okay, and here we are assuming that E is equal to 1 for both the wing and the tail. So we'll get CL alpha 3D is equal to 5.5581 1 plus 5.5581 by pi into 6.06. So this comes out to 4.302 per radian. Okay, so this is for the wing, and now we'll also calculate the CL naught. So so from here you can see that the alpha at zero lift, this is minus 5 degree. So with this we'll calculate the CL naught. So CL naught will be CL alpha into mod of alpha at zero lift. Okay, so this is 4.302 into, so when we use CL alpha we have to use the 3D value of CL alpha, 4.302 into this is 5 degrees. 5 degrees we have to convert it into radians. No, sorry, divided by 57 point. So this comes out as 0.375 radians. No, sorry, not radians. This is just the CL naught. Okay, now we come to the tail. Now again for the tail, we first find out the aspect ratio, which is b square by s, and this is 13 square by 43. So here the tail area is given as 43 feet square, and the tail wingspan is not given. So I have assumed it to be 13, 13 feet. Okay, so you can assume this that b tail is equal to 13 feet. So this gives a aspect ratio of 3.93. Yes, we can also calculate work in degrees also. That is not a issue, but you have to then be consistent. Like all the everything, everything has to then be in degrees. Like CL alpha, and CL alpha, everything has to be in degrees. If you work in degrees, then CL alpha has to be in degrees. Now here the CL alpha 2D, this is 0.01 per degree, so we convert it into radians. And now similarly we find CL alpha 3D using the same formula. Here also we assume this as 1. So this comes out as 3.91 per radian. Okay. uh, 0.57. Acha. Okay, then there must be a mistake. Okay, I think there is a printing mistake. This should be then 0.0.1 per degree, because otherwise the CL alpha will be too low. Okay, like you can see that the CL alpha for the wing is 0.097, and if for the tail this is 0.01, then it is 10 times lesser. Okay, so like this, like the magnitudes are not the same of the same size. So I think this will be 0.1 degree. And anyway, like I have so I've taken this example from Nelson's book. Okay, Nelson's book. Okay, and so he has used this 5.73 value for the rest of the calculation. Okay, now we'll calculate the wing contribution and the tail contribution. So wing contribution and tail contribution to what? To Cm naught and Cm alpha. Wait, so Cm naught wing will be uh, Cm AC wing plus Cl naught wing into x bar Cg minus x bar AC. Okay, so you know that like this is the aircraft. So if you have the wing over here, so AC, oh, sorry, the AC of the wing is placed in front of the CG. Okay, like this. So there is a CM AC wing acting in the negative direction, and the lift of the wing, it acts in the positive direction. So if I now draw a bigger picture of the wing, so this is the AC and this is the CG. Okay, and there is a negative moment which acts on the like the wing is consists of a cambered aerofoil, so it produces a negative moment, and the lift produces a positive moment. Okay, so both of these things we have to add. So the CMAC comes from like this section is consists of the CMAC, and the lift creates this second term. Okay, CL not wing into this, and the Cm alpha wing, this is equal to Cm alpha wing is equal to Cl alpha wing into x bar Cg minus x bar Ac. So now you can put all the values and calculate everything. So Cm not wing will be you check over here. This is CMAC is minus 0.116. CL naught we have calculated as 0.375 into x bar Cg is given. So x bar Cg was this 0.295 C bar, and x bar AC, that is also given 0.25 C bar. Okay, So you can now calculate the value. Uh, so this comes out to minus 0.099. Okay. So this is the wing contribution. Acha, no, we have to calculate Cm alpha of the wing also. So Cm alpha of the wing is Cl alpha wing into this. So Cl alpha wing we have calculated 4.302 per radian. So this comes out to 0.1935 per radian. Okay. Now we'll calculate the tail contribution. Same like we'll calculate the Cm naught and the Cl alpha of the tail. So how does the tail produce a moment? So primarily, if this is the CG of the aircraft, the tail produces a lift, and this lift, when it acts in this distance, it produces a moment like this. Okay. So this is the mechanism how it produces a moment. So in this case, first we'll calculate epsilon naught. Epsilon naught is 2 CL wing naught by pi aspect ratio. So this comes out to 0.04 radian. So all these things you know. So wait, this will be CL not wing. So to this CL not wing, you know, this value 0.375, and aspect ratio of the wing also you know, which is 6.06. Next we have to also calculate d epsilon by d alpha, and this is equal to 2 CL alpha wing by pi aspect ratio. So these values also you know. CL alpha wing, you know, it is uh, this 4.302, and aspect ratio you know is 6.06. So now you can calculate this as 0.45. 0.45. Next we have to calculate the horizontal tail volume ratio. So this is equal to LT ST by S C bar. So you can substitute all the values and calculate this. So LT is the distance between the uh, LT is the distance between the aerodynamic center and the uh, it is the distance between the tail aerodynamic center and the CG. Okay, so that value is given here. So LT is 16 feet, and the tail surface area is also given as 43 feet square. Uh, wing surface area is given as 184 feet square, and the wing chord length is also given as 5.7. So if we substitute the values, it is this is 16 into 43 by 184 into 5.7. So this is 0.66. Okay. Now with these values we can calculate Cm naught and Cm alpha of the tail. So Cm naught tail is given as eta Vh Cl alpha tail into epsilon naught plus setting angle of wing minus setting angle of tail. So you can calculate this. Eta will assume as 1 and this was 0.66 and this was 3.91. Epsilon naught is 0.04. Uh, Setting angle of wing is 1 degree and setting angle of tail is minus 1 degree. So it is 1 plus 1 by 57.3. So why this? So these were given in degrees and this is in radians. So I am converting this into radians. So now you can calculate everything. Okay, so this is the Cm naught and Cm alpha contribution of the tail. Now we'll calculate the neutral point. So x bar np. So x bar AC was given. Okay, this was given as 0.25 C bar. Then eta we are assuming as 1. VH was 0.66. CL alpha tail was 3.91. CL alpha wing is 4.302. So when you put all these values, you'll get 0.58. So this is the location of the neutral point. Now we'll move on to the next question. This is the next question. So this is a bit complicated question. So we have been given some data where the aircraft was trimmed at different speeds. And for this question, assume CL alpha is zero point 0.1 per degree. And so in the data, you can see we have been given speed alpha CL, elevator deflection in degrees, and the position of the CG. So this is x bar CG. And we have to calculate x bar NP from this data. Mm, okay, so for this question, we'll use a formula which is elevator deflection is equal to, okay, and further we'll use this formula. So delta E naught is equal to Cm naught by Cm delta E negative, and d delta E by d CL trim, this is negative of static margin by Cm delta E. Okay, and further we can write static margin uh, is equal to this x bar NP minus x bar CG. So substituting this, we'll get this formula which, okay, so we'll get this formula. Acha, one more thing, we can actually let this be. Okay, we can actually write this as delta E not only. We don't have to substitute. So we'll get this formula. So we have to substitute the values and find out uh, position of x bar NP. So what we'll do is we'll first take two cases. So let us take the first two cases. So here the delta E is a minus 3 degrees and 1 degree. So let me write here minus 3. So you notice here that here I am working in degrees instead of radians. So delta E naught we do not know. X bar NP we have to find. X bar CG we know. It is 0.3. CM delta E also we don't know. And CL trim we know it is 0.5. So this is one case. Another case is the second row, which is 1 is equal to delta E naught minus X bar NP minus zero point 0.3 by Cm delta E into zero point 0.3. Okay. Now what we'll do is we'll subtract one equation from the other. So let us subtract the first equation from the second. So we'll get 4. So these terms will cancel. Okay, delta E naught will cancel. And we are subtracting this term from this term. So we'll then get X bar NP minus zero point 0.3 by Cm delta E into 0.2. Hmm. Next, so this was the first two rows. Now we'll similarly do for the next two rows and we'll get another value. So the next for the next two rows we have delta E 0 and 1.5. Now again we'll subtract the first equation from the second and these terms will cancel and we'll get X bar NP minus 0.4 by Cm delta E into 0.3. So we get these two equations. Now you can see that in these two equations there are two unknowns. So we can solve and find X bar NP. So let us say that we divide one equation by the other. Okay. So let us uh, let us divide the first equation by the second. So we'll get 4 by 1.5. Hmm. So the Cm delta E has been cancelled. Cm delta E term has been cancelled. Now we can solve this equation and find out X bar NP. So firstly, like we can So this is the answer. So the neutral point is located at 0.4333. Okay, now moving on. So these are the rest of the exercises. So this question is that when the center of gravity of the aircraft is moved rearward, then the effect on the long period mode will be. So as you know that when you uh, as you know that to make the aircraft more stable, the CG has to be in front of the AC, right? So as you know that this is the CG. If the situation is like this, that the CG is in front of the AC, then the aircraft is stable. So here I am aircraft is pointing in this way. So if the situation is like this, then the aircraft is stable. But you know that if the opposite, if the case is opposite, that the AC is in front of the CG, then the aircraft becomes unstable. Okay, so you know that when the CG is moved back, it decreases the stability of the aircraft. When you move the CG forward, it increases the stability. When you move it backward, it decreases the stability. So actually, this point should be, this point is technically called the neutral point. But the neutral point is like the weighted average of all the aerodynamic centers. Okay, so it means the same. Okay, uh, so if you move the CG backward, then it becomes less stable, and if you move it forward, it becomes more stable. So therefore, in this question, it will be less stable. This is the next question. So here, as you know, that the necessary condition of a stable aircraft is Cm alpha less than 0. Okay, Cm alpha less than 0. So for stable aircraft, you want Cm not greater than 0 and Cm alpha less than 0. This is the next question. So this is actually similar to the previous question only. Uh, it just says that in what condition can you hold the aircraft stable at a positive angle of attack. So the previous thing that we saw, Cm alpha less than 0, this will only ensure that the aircraft is stable, but it will not ensure that the aircraft will trim at a positive angle of attack. Okay, so it will not ensure that the aircraft is trimmed at a positive angle of attack. Okay, it might happen that the aircraft is stable, but it is stable pointing downwards. Okay, so this is undesirable because usually the wing of the aircraft it produces lift at a positive angle of attack. So we want to ensure this case and not this case. So we need another condition which is Cm not greater than 0. So therefore here the answer will be this one, which is Cm alpha less than 0 and Cm not greater than 0. Now here there is a similar question that at what condition can we hold the aircraft stable at 0 angle of attack? Okay, so this is quite intuitive actually. So in this case, Cm naught has to be 0. So if this is the Cm versus alpha curve, and then this is Cm naught, and this is alpha trim. So the point where this curve it crosses the x-axis, that becomes the alpha trim. So if Cm naught is 0, then the curve crosses the x-axis at 0, right? So then alpha trim is equal to 0 and Cm naught is also equal to 0. So therefore in this question the answer is this Cm alpha less than 0 and uh, Cm naught equal to 0. Okay, now moving on. So this is another question. So this question says that for a fixed wing UAV, the tail area is 1/4 of the wing area, and the wing and the tail are rectangular in shape. And the following data is applicable. So the weight of the aircraft is 550 kg, the cruise velocity is 35 meters per second, the rho is 1.2256, this is sea level, and CL alpha wing is given, CL alpha tail is given, alpha at zero lift is given, chord length C bar is given, uh, B of the wing, so the wingspan is given, and Cm naught of the aircraft is given, and your eta tail is given, and x bar AC is 0.32 meters and x bar tail is 2.925 meters, and tau is zero point 0.4, d epsilon naught by d alpha is 0.375 and epsilon naught is 0.75 degrees. So so this is the data. Now we will see the questions. So this is the first question. So the location of the neutral point in meters of the above fixed wing UAV from the leading edge of the wing is. So let me go back. So we have to find out the neutral point in meters uh, from the leading edge of the wing. So this is the data. Yes, you have to find the neutral point. So let me proceed here. So XNP. So notice here that I have not written the bar over here. Uh, so I'm writing this in absolute units, not in not this is not divided by the chord length. This is CL alpha wing into X AC wing. So all of these values are given, so you can substitute. And one more thing is that uh, achha, okay, no problem. So this is 5.056, X bar receiving is 0.32 meters. This is 0.89, I think. ST by S is 1 by 4. So ST by S, how do we get? It is not written in this data. It is written in the paragraph that tail area is 1/4 of the wing area. So from this we know that ST by S is 1 by 4. This is also given 0.375. XAC tail is given as 2.925 meters. And the CL alpha wing is 5.056 plus 0.89. So we have to also write the CL alpha tail. CL alpha tail is 3.38. So now you can calculate all of this. So this comes out as 2.99 by 5.52. Okay, so this is the answer. Moving on, so this is the next question. The total lift curve slope of the UAV in per radian. So basically you have been given CL alpha wing, you have been given CL alpha tail and all the parameters of the tail. So you have to find CL alpha of the aircraft. So you have to, in a way, you have to sum up the contribution of the wing and the tail. Okay, so okay. So now we have to calculate the CL alpha contribution of the wing and the tail, right? So for this, we will use the formula that CL alpha of the aircraft is CL alpha of the wing plus eta tail St by S CL alpha tail. So all the values are given, you can simply substitute. So this is so this comes out as 5.526. Moving on is the next question, that what will be the static margin. So let me again open the, so you can note down this. So XNP was 0.54 and CL alpha of the aircraft was 5.526 per radian. And now we have to find the static margin. Okay, one thing. Okay, so see, in one more data was missing here. CM alpha of the aircraft, this is -1 per radian. So this is also given CM alpha. So for this, we will use a relationship that static margin is equal to minus dCm by dCl. Okay. So this is a relationship that you know. What we can do is we can use chain rule. So we can write something like this. So we can also write that static margin is equal to minus Cm alpha by Cl alpha. Okay, and all the values are given. So Cm alpha was minus 1 per radian, and Cl alpha we calculated here. This was 5.526. So this comes out as 0.181. So actually there are no answers which match it. So this is the closest one. So the static margin is 0.181. Next question is this. With the static margin obtained in the question, so static margin obtained in the previous question, what is the location of the CG of the UAV in meters? Okay, from the wing leading edge. So you have to find out XCG. Like be careful, like you do be careful that you have to find out XCG, not X bar CG. And the rest of the things you know, the static margin and the neutral point. So for this question, I'm going to use the formula that static margin is equal to x bar np minus x bar cg. So this you can further write as x np minus x cg by c bar. So then you can find solve for cg. So then you can solve for xcg. Uh, xcg is equal to xnp minus c bar into sm. Hmm. Again, you can put all the values here. So this is 0.54 minus c bar was given as, where is c bar? C bar is 1.2 meters. 1.2 into 0.181. So this is 0. No, this is 0.322 meters. Okay. No, SM was not negative. It was positive. Actually, there were two negative signs. They cancelled. CM alpha was negative. Okay, this is the next question where you have to find the horizontal tail volume ratio. So, excuse me for some time, like I'm coming after 5 minutes. Okay, let me see. Vertical tail volume ratio, this will be LT by C bar into ST by S. Okay, so or you can say that ST by S you can put in front. So ST by S is given as 1 by 4 and LT will be uh, XAC tail minus XCG by C bar. So this is 1 by 4 XAC tail, it is given to 2.925 meters. XCG we have calculated as this 0.322 and C bar is 1.2. So this comes as 0.542. Okay, so that is it for today. So thank you for joining.